Hey everyone, and welcome to Summarize Science. Generative AI can now produce incredibly realistic synthetic data for fields like healthcare, finance, and public policy. While this is great for research and development, it also creates new risks. This high-quality fake data could be used for fraud, to violate copyrights, or to mislead important decisions. So a critical question has emerged. How can we trace where this data came from to ensure accountability? A promising solution is called watermarking, which embeds an invisible statistical signal into the data before it's released. Think of it like a secret fingerprint that only someone with a special key can find. However, existing methods for tabular or spreadsheet-style data have faced major limitations. They were often slow, couldn't handle mixed data types like text and numbers, or the watermarks were too easy to break. This paper introduces a new method called TAB-DRW, a clever and robust way to solve these problems. Instead of just tweaking the data directly, it first transforms each row of data into the frequency domain. This is conceptually similar to how an audio signal can be broken down into its constituent frequencies or pitches. The system then embeds a secret, pre-computed pattern of bits by adjusting specific components of this frequency representation. This process is designed to be subtle, preserving the quality and usefulness of the original data. The generation of this secret bit pattern is also a key part of the innovation. It uses a secret key to select a few columns and then calculates a unique rank for each row based on their values. This rank determines the specific bit pattern for that row, which is stored in an implicit binary tree structure. This rank-based approach means the system doesn't need to store a massive list of keys for every single row, making it highly efficient. It also makes the watermark very resilient because small, random changes to the data are unlikely to change a row's overall rank. The researchers put TAB-DRW to the test against 4 other leading methods across 5 different real-world datasets. First, they measured data fidelity and found that TAB-DRW introduced minimal distortion, keeping the data's quality nearly identical to the unwatermarked version. But in terms of detectability, it was a clear winner, achieving the highest z-scores on most datasets, which is a statistical measure of how strong and unambiguous the watermark signal is. But what happens when someone actively tries to destroy the watermark? The team simulated 10 different kinds of attacks, including deleting rows and columns, adding random noise, and shuffling the entire dataset. Across the board, TAB-DRW consistently demonstrated superior robustness, with its watermark remaining strongly detectable while others failed. They even simulated an adaptive attacker who knows exactly how the watermarking method works, but just doesn't know the secret key. When this attacker tried to erase the signal by re-watermarking the data with different keys, the original watermark from TAB-DRW remained highly detectable. So, to recap the key points, the TAB-DRW method provides a lightweight and robust way to watermark synthetic tabular data. It preserves high data fidelity, meaning the data remains useful, while embedding a signal that is both highly detectable and resilient to attack. This is a major step forward for ensuring data provenance and accountability in the age of generative AI. Techniques like this could become essential for protecting intellectual property, fighting financial fraud, and ensuring the synthetic data used in critical fields is traceable and trustworthy. It offers a solid foundation for the future of secure data sharing and the responsible development of artificial intelligence. Thanks for watching Summarize Science.